Yeah, thank you. So I hope I can cover both like the more general topic as well as some technical details for the ones who like to dive into bytes and so on. So short, who am I? My name is Yuri Gbur. I did my master's thesis at the TU Berlin, and most of the stuff I'm talking about today resulted from the research related to this thesis. Currently, I'm a security consultant and a SecConsult, and I have my head mostly in the clouds there. So some quick background, and I promise it's the last pun. What are we doing with QUIC, or why is it interesting, and why should we care? So QUIC is, from what it does, a transport layer protocol primarily. And it was recently standardized by the IETF, and it was also to be chosen to be the core fundamental protocol for HTTP3. And this means we have one of the biggest changes to our web network stack for like over the last 20 years. And we also see that we have a lot of interest by big companies that are developing implementations, and we see that it's gaining a lot of traction. So that's why we're talking about it. So how does it look like? So we now have the ability with QUIC to combine the stream abstraction that we know from TCP with the security and encryption capabilities of TLS into one layer, as well as some multi-streaming. And this allows us to have a much faster connection setup, which is interesting for real-time applications, for example. But to be compatible with our current network stack, it's built on top of UDP, which technically makes it an application layer protocol and not a transport layer protocol, which is interesting, and I come back to that later. Some core concepts. So this at first might look a bit daunting. Okay, what do we have? Everything new. But if you look a bit closer into all these messages, we see, okay, we have our three-way handshake we know from TCP, so nothing really new here. They're just called initial messages. And then if we look into the frames that are transmitted in these messages, for example, here the crypto frames, we see we have all the stuff we know from TLS, server hello, client hello, and our key information. And QUIC does support TLS 1.3 and also zero round-trip time resumption. One fairly unique feature is connection migration. This allows, as we are built on top of UDP, that a client can change the IP address and the port, and still the connection can be maintained. And this is done that the server, upon receiving or detecting a migrated client, sends a path challenge with a token, and the client reflects this token, validating the new path. So, what are some general security challenges we have? First, we're now living in the user land. This is interesting or nice from a developer perspective, as we're now able to deploy much faster, as we don't have to do changes to the kernel to do changes in transport layer functionality. But, of course, on the other hand, we will miss some things we know from common TCP-based communication. For example, common syscalls, we have TCP. Then we have the much larger attack surface. So as we're living in the user land, we usually have weaker security boundaries, and we now have multiple libraries and vendors basically developing the same network layer transport or transport layer protocol functionality, which means we have more room for bugs and errors there. And if we're getting away from the host to more like the network parts, looking at transport layer firewalls, so short reminder, we usually have two approaches, very simplified. We have stateless firewalls, where we just say, okay, we have static matching of, in this case, IP tables, ports, and the protocol, and we either allow or deny a packet to go through. Then we could supplement this with a stateful approach, where we have a state table, in addition, that tracks connection states. So this is meant so we can say, okay, only new connections can come in, or only established connections can go out. And we can do this with TCP because we can see the relevant flags in TCP that allow us to track connection state, like SYN flags, the sequence numbers, and the acknowledgement, and so on, or the FIN flags for the teardown. And if we now look to UDP, which we have with QUIC, we don't have this anymore. Because with UDP, we don't have this information of state because it's implemented above in the QUIC layer now. And therefore, every packet, for example, coming back from the other end will update our firewall, or will be said, okay, this is now an update, or it assures our connection. And we additionally don't have any teardowns, so this means we only have a timeout, and this means as an attacker, for example, we could keep open like this holes forever, indefinitely, by just sending matching packets. And this is like a technique that is well known for a long time. It's called UDP hole punching. And we will now see an increase of relevance again, because with this, we will now have the possibility with QUIC, as it's widely deployed, to have, for example, data exfiltration or some certain firewall bypasses, or like here in this example, we can use this hole that we created through a legitimate connection for initiating reverse shells later, if we're able to get to the port or like on the target. Okay, what could we do? We could look deeper into the packet, implement all the functionality of QUIC, and then everything is fine again because QUIC does the same, right? No, of course not, because we now have QUIC, which makes security and privacy like a first-class citizen. So much or most of the relevant header data is encrypted as well. So we don't see the SYN flags, for like the equivalent. We don't see the acknowledgements. We don't see the sequence numbers. This has a significant impact, on one hand, on routing, optimization, and load balancing. And it has been shown in the past that this can be used to bypass certain load balancing approaches, directly targeting hosts and making more efficient DOS attacks. And if we now look in the application layer security side, where we could even decrypt it, going one step further, we still see that we have an issue with our current tooling, as most web application firewalls at the moment do not support QUIC and do not support, or like the HTTP3 standard, and do not support the multi-streaming that is now in QUIC. And also for like the offensive guys here, we also see an issue with our tooling. So we cannot have the same sophisticated methods or testing with QUIC servers or HTTP3 servers, as most of our tools do not support QUIC at the moment, and their like alternatives are really sparse at this moment. So we need to ramp that up and get more tooling working. We also did like an overview DOS taxonomy that we have with QUIC that we can directly resolve or like derive from the specification. And we see that we have similar attack patterns, like here the client initial flooding and the resource depletion that is similar to SYN flooding, but we also see new attack techniques like stateless reset oracles, which is, I can't go into much detail, but have a look at the specification if you're interested, that works on a mechanism that is only present in QUIC. And of course, the tooling we currently have does also not support or detect or protect, in this case, against these DOS vectors. And we looked more deeply into two of them, and I come back to that later, because now the primary part of our research in QUIC was request forgery, where we looked into an attacker as a client side, and we wanted to forge a victim, the QUIC server in this case, to forge a message to our target. And we do this for two primary reasons. We either want to bypass network restrictions to address internal targets, for example, or we want to utilize the resources of the victim, for example, more bandwidth. And we found three primary techniques in QUIC. First one utilizes the connection migration mechanism. So there we established a valid connection, and at some point we spoof our source IP address or port, and then the server, which is not able to determine if this is a valid migration, will send this path challenge to the target. And we can do a similar approach directly in the server initial messages, where we spoof our first packet and the server thinks, oh, this is a new connection attempt, I will send my server initial packets. And one variation of this is the version negotiation mechanism, which, where the server, upon receiving a version it does not support, will answer with a packet that contains the version set to all 0 bytes and then a list of all the supported versions. And why this is interesting in particular, I will show later. Because we looked into protocol impersonation, also known as cross-protocol request forgery, where we want the target to interpret a packet, a UDP packet, as a different protocol. So we forge a QUIC packet, but it's then interpreted, for example, as DNS or something. And therefore, we looked into the controllable bytes basis of the packets. And we saw that most of them are very, very limited, as mentioned, because a lot of it is encrypted. The primary target is the so-called connection ID, short CID, that is used to identify QUIC connections. And we sometimes have only one, the destination connection ID. And at some points, we have two of them, as the client can propose a connection ID that is used by the server. And in total, we have 20 bytes. This can be up to 20 bytes for the current version of QUIC. But this version negotiation mechanism that we see on the top is interesting because we have two special parameters here. First, that the CID can have the entire length that is possible to be encoded in 1 byte, so 255, and the server must reflect the CID that is proposed by the client. And this results in 512 bytes, controllable byte space, with some trailing and prepended uncontrollable parts, but we will show that this is still enough to impersonate some protocols. So here we see this in action. We have the bytes of a packet. On the top hand, we have the QUIC interpretation. On the bottom end, we have the DNS interpretation. And we see we can work around here because the flags that are not controllable result in the DNS ID. That is, can be fairly arbitrary, that's nice. And then the 0 bytes that result in the DNS flags are all 0, which is okay, it's still a valid query, and we can work around that. And then we can control the first byte of the query amount, and we set this here to 7, not because we want to send 7 queries, but we have to skip over some parts to land in the queries. And there, if someone is familiar with ASCII, you can see 74752D, which is TU minus Berlin, of course. Looking at this in action, we have a Wireshark capture here from the same network traffic on the left and the right. On the left, it's the QUIC interpretation. On the right, it's the DNS interpretation. And if we enlarge the left one, we see, okay, we have this initial message here that where we, as an attacker, spoof the source IP address of the Google DNS server, 8888, and of course the port 53. And then we see this server, as intended, sends this version negotiation packet that is a valid version negotiation to the DNS server. And then we get something from the DNS server back that does not make sense in this context. But looking at it in the DNS interpretation, we now see, okay, this is a valid standard query that we sent, that we forged, and the server indeed answers us and sends us back the standard query response containing the IP addresses. And this could be used for examples to improve timing in DNS cache poisoning attacks, or you could use other protocols like NTP if this is possible. For example, you could think about internal amplification attacks. So this is only a proof of concept, and I think there is a lot of other stuff that could be done there. So, yeah, what could we do about it? Currently, there isn't a mitigation mechanism. So we propose 2 mechanisms. First, hashing, so we hash the CID. Therefore, the attacker would have to calculate the inverse of the hash, which should be infeasible, of course. Or we could add an additional header field where then this value in this field is chosen by the server and XORed over the entire header, similar to WebSockets, as in a masking approach. Yeah. And the second attack vector we identified as traffic amplification. So here our goal is to send more data from the victim to the target than we have to send from our attacker. And we look primarily on the path amplification here. This means we look on the data we have to send on the unvalidated path. We do this because we can directly compare this to the specification that says, okay, it should not be able to send more than 3 times the amount of data received on any unvalidated path. And therefore, we look deeper into the specification and identified 3 primary pitfalls here. So the first one is that QUIC also must support or must check that, that it can support up to 1,200 bytes datagrams, and we see that this would conflict with receiving a small acknowledgement on the connection migration and then sending 1,200 bytes. This will definitely surpass this limit. And therefore, there's an edge case that is defined. It's a bit hard to find, where it says, okay, the server should send 2 path validations, first one to validate the path itself, and then the requirements. And of course, as you all know, the server handshakes for TLS are much larger usually. We see that too here, that it can happen that, of course, that the server initial messages are larger than the client packet sent, and thereby bypassing, or not bypassing, surpassing this limit. And both of these get worse if we look into reliability, because if one packet already violates this limit, if I send multiple or resend my packets, I will increase this issue. And yeah, what can we do about it? As mentioned, RDFM, it's in the specification. So there shouldn't be an issue, but of course, if we look at the data, there is. So we looked into 13 open source implementations of QUIC and evaluated these techniques, and we found that 5 of them were vulnerable to this path amplification, sometimes really significantly, so this is log scale on the left. So yeah, and we of course notified all the vendors about it and should be fixed by now. So nothing, 0-day drops here. So yeah, so in conclusion, what did we see? We see that we have a greater attack surface with QUIC and more room for errors because we live in the user land. We see with UDP hole punching or similar that old vulnerabilities become irrelevant again because we have this protocol change. And furthermore, we see that we have poor tooling support at the moment, both on the offensive and defensive side. And I think we should really get that started to improve this tooling here because Google, especially Google, is already using QUIC a lot. And currently, with multiple implementations as shown, we see that there is a significant discrepancy between the specification and the implementation, likely leading to bugs and possibly vulnerabilities. And also, besides that, we still have issues with the general protocol that we have novel attack vectors like this protocol impersonation that are possible in QUIC that have no built-in protection mechanism at the moment, and we still have to wait for an upcoming version to fix that finally. Yeah, so with that, if you want further reading, feel free to check these out. This is the paper from the NDSS where we published the request forgery and also some other tech reports and blog posts. Thanks for listening. Yeah.